Hello, welcome back to the class. Today we will talk about this class called Keypoint Localization, which is actually one of the main ingredients for the image search. So I hope that at the end of this today lecture material, I wish that you can understand, you know actually some of the related conferences, so that you can find some of the papers, which will be helpful for you to conduct this project. And also I wish that you can understand the locally invariant features along that line. We will talk about the key point localization. As in some of the examples, we also briefly touch on the Harris corner detector. Before we move on to the today's lecture material, I'd like to review what we talked about last time. Last time I talked about the different student activities, including the paper presentation, also this mid and final term project presentation. I wish that based on these activities, I wish that you can get some of the research related experiences, and then you can get some of the next publications. And we talked about the grading policy. It seems that actually there are actually not many students actually that attend register this course. I think that you can do this single man project. So let me remind you some of the homework for every class. So I recommend you to go over the next lecture slide. Just spend 10 minutes, 20 minutes, something like that. So in that way, you will be ready for taking the next class. Also, try to come up with one question on what we have to discuss today. So as I mentioned before, I will go over all of your questions. I will give some of the score, but don't worry about the score. So most of case, you will get your question will get 1. Further questions we thought, that surprised me, I will give 2. But do not aim for getting the highest score. Basically, it's not that big of deal given this overall grading system. But the main reason why I'm having this one is that I'd like to encourage you to come up with good questions that might lead to your next research activities. Also, since we are doing this offline video lecturing, I'd like to hear about your questions about this lecture material. So overall, you need to write down the questions 3 different times before the midterm exam. So basically, do not write the multiple question in a single time, since at that case, even though you actually had multiple questions, they will be counted as one time. So basically, once you hear the lecture material, when you have some questions, just write down one question. That will be enough. And also, the common questions actually already identified and also addressed in my ongoing draft. Also, also some of the questions will be discussed in the class. But if you want to hear basically we are not focusing on answering your questions actually. The main reason is that we all of us actually very well trained to answering the questions. But the more important issue is that posing up the great questions. So we will focus on the coming up with questions. But if you want to hear about the answer to your question, let me know, and then I will actually try to answer the question. And we actually having this homework, right? Every week you need to go over the 2 papers and write down their summary, right? So you need to basically you need to be able to find some of the recent paper related to this image search, also related topics. And I wish that you can find high quality papers. But basically the papers published at the top tier conference, usually they're in high quality, right? So you can find the paper from the computer vision field, CBIR, ICCV, ECCV are some of their very well known computer vision conferences. Also, there are actually dedicated conference on the image search, image retrieval, or the multimedia retrieval. Some of them including this ICMR. Also, there are a lot of these image search techniques, borrowing the machine learning techniques. So you can also go over some of the machine learning field, the conference, NeuralLeaps, ICML. Also, this is the multimedia one, also CBIR, which are also more or less the application related the conferences. So I wish that you can find the recent papers. So basically, mainly for paper presentation, you need to do the, after midterm exam, you need to present 2 papers, something like that. For those papers should be published since the 2016. So there, I wish that you can actually go over the paper, those recent paper. But for these papers of abstracts, the summary submission, you can find the more older one. But in the end, you should aware that in the end you need to present recent papers. Basically, broad. I do not actually assume you go over all the details about the paper. Just find the broad 2 papers, and basically, by doing that, I wish you can find your research topic for this project for the project in this course, and submit to summary before every beginning of the Tuesday class. So this submission should be done by the next week Tuesday. And online submission as possible. You can find the link in this lecture material at the end of the slide or through our this homepage. And here actually, when we actually have many students, usually I encourage you to have multiple people get together and do their project together. But there seems like we don't right now we have the student less than 10, so you can do the solo project. So you can if you actually had a research that are related to the image search, you can bring that research topic to here, as long as that topic actually relates to this in some way to the image search. I actually show this slide, the image search or content-based image retrieval. Nothing but identify similar image given the user-specified image or other types of input. So basically, we provide the input, the query image, then we wanted to go through the web-scale image database and identify the semantic, visually similar or the semantically similar, depending on your applications. And basically, we can look at the RGB, raw RGB, look at the RGB channel, but actually this RGB value itself varies a lot depending on the illumination level and then in what direction you are looking at the model. So typically we extract the image descriptors. Some of the well-known old image descriptor is a SIFT. You might have heard about this SIFT, but the recent one is that actually convolution, the deep learning based approach, this convolution neural net based feature, deep learning feature actually works quite well, even actually outperforming the manually created this classical feature like the SIFT. So these are some of the key components of image search, and obviously we'll talk about image representation, indexing structure, matching algorithm. Also, there are many related techniques to the image search. You can use classification, localization. These are actually mainly studied in the computer vision field. You can actually, based on the image search, we can even improve this classification localization. Also, we can also adopt some of this classification localization to the image search and improve the quality of image search. So you can do any kind of the research project if they're actually related to some of these kind of topics. Mainly we will talk about the image representation. Some of the classical approaches actually SIFT, the GIST, as I mentioned before, recently the CNN is becoming very popular. These are actually invariant, designed in a way to invariant to different transformations. Different transformations, there could be many cases. I will talk about it later on. But here, once we actually extract the feature, I will talk about what we do for the image retrieval. Basically, at pre-processing time, given the image database, we build the database for the efficient retrieval at runtime. In the end, given the user query, we wanted to return the search result within the fraction of second, right? So that because of that, we need to have some sort of very efficient database. So suppose that if we had many images, we need to also extract the feature from each individual the image, and then we need to somehow encode them in a very efficient database. So they actually suppose that if you had 1 billion image, then obviously going over all those 1 billion image descriptor takes a lot of time, right? So there should be some sort of very efficient way of searching this image database. as an example, there are many different index schemes. We'll briefly touch on this vocabulary tree, which is it's kind of old, but a very well-known technique. Some of recent technique comes with the hashing technique that also compress the image descriptor, so that actually we can lower down the memory requirement. Also, there are inverted files. We will get back to that issue later on. And then once we build that kind of the indexing structure, at runtime, given the core image, we actually going over the database. We can then actually identify similar images actually. And typically we actually identify short list, right? If you do the Google search, given your query, it identifies the sum of the web page, right? Actually, those are the short list. Typically, we can, for example, we can actually identify 10 similar images, right? Given the query, the user can choose actually whatever he or she wants, right? But sometimes, given the query, we might get a very well-matching image here, but they're actually somewhat different. Also, you can suppose that this was a well-matching one, but somehow this actually the ranked lowly in this list, right? But obviously, user takes a lot of time to going over each individual short list to that one, right? So it's actually more desirable to push this kind of well-matched similar image up in the list, right? So typically we do the actually re-ranking through the different types of the technique. One of very well known is the spatial verification. Basically, this spatial verification is that we look at actually what are the different image paths, and then we look at what are their geometric configurations. By matching them, by considering them, we can actually get a better result. We will get back to that issue later on. But if we do that, we hope that actually we can push up the similar image higher in the list, higher in the short list, so that actually user can identify the similar image in a shorter amount of time compared to this initial result. So these are some of the main steps and of this image search. Do you have any question? By the way, actually, I know that this offline video actually lacks interaction between me and my students. So in the hope that to improve this interaction, I try to invite one student, mainly from my lab, so that actually I can get some interaction with them, and then I hope that interaction give you also address some of your questions. Do you have any questions so far?
Actually, recently I read a paper about how CNN understands image. It said that CNN understands an image because of its texture instead of shape.
Shape, yeah.
Yeah. I think, but when I look back on existing research, it often use hash clause to compress the image. I think things affects it, but recent work often hash work combines with CNN.
Mm-hmm.
I think it may affects their ability of.
Okay, you said hash or the.
Hash over CNN.
Hash over CNN. Okay.
Yeah.
So basically, what he said is some of the recent technique. We didn't actually talk about the low level the different technique yet, but he actually know some of the recent CNN technique, the deep learning based approach. The deep learning also I mentioned that deep learning based approach also serve as a very good image descriptor. Basically, they also the CNN descriptor also the responding capture the characteristics of this image, some of semantic information, also text information, but not that much of this spatial the relationship between different parts, right? I think that that's actually one of the very interesting research area. How we can consider this geometric information on top of this deep learning technique. That will be the very interesting research actually. The question, if you want, you can do your research along that line. Okay, so but why? I mentioned that the raw RGB itself is not a useful image descriptor. Why? basically there I mentioned that the RGB is not robust for various changes. Further, this at high level there are geometric and photometric transformation. Suppose that there are same book here and there, right? But they're basically that we actually looking at that book in a two different angle, right? Even though actually if you look at the same patch, actually they are same thing, right? And even though book looks looks very different, right? But if we can identify this small patch here and there, and then if we somehow align them in a canonical space, then you can see that even though this RGB image is very different, actually we can get this very similar vision, right? So basically the RGB itself, the original image itself is not really robust for this kind of geometric information. They look very different, but somehow if we do some sort of the transformation, then we can get some reasonable basically that we actually get a very similar patch, right? That's actually you can treat that this kind of the local image descriptor. Another one is photometric one. So the same book, but depending on your illumination color, then the actual image of the book looks very different, right? So basically, ideally we wanted to have the image descriptor that are robust to this geometric transformation and photometric ones. So there also at high level image descriptors classified into the global feature and local feature. The global means that given this image, we only extract only one image descriptor. The local feature is that given this image, we extract the different parts of the local patch, and for each patch we actually compute this local image descriptors. So basically, if we can for a local feature, if we can extract 100 patches, and for each patch if we create this image feature, then we can create 100 different local image descriptors. At high level, the global feature usually encode the overall context, right? So they're sometimes really very useful. But in this class, for now, we will mainly focus on this local feature, since actually this local feature can encode the different parts of the scene and object, right? And by looking at this many local feature, we can improve this image search, right? So actually, that's one of the main reasons why we are using the local feature a lot for the image search. But usually, for achieving high accuracy, we usually combine them we use them together, global feature along with this local feature. We will get back to that issue later on. But for now, just we will focus on explaining this local feature. Why we need to think about image descriptor also local feature? I already mentioned that this geometric transformation, same object, but depending on the viewpoint, it looks different, right? But for that case, actually, maybe the geometric descriptor will just extract only one feature might be enough to identify that actually they are same thing, right? In that case, you might need a local feature. Illumination change, same one, but depending on illumination, they looks very different. Or scale change, when you think about scale change. Also deformation. Even in this case, actually, this is one of the example why we need to have a local image patch. So in this case, actually, most of part actually they are same thing, right? But there are some regions, local regions actually they looks very different, right? So if we just extract only one feature, global feature, we might say that they may be same or the different one. But actually, if we extract many local features, we may know that some of patch local descriptor from here, they actually the same to this part, but only this region may be different from there, right? So based on that, by using the local feature, we can get more information. Occlusion. Occlusion is one of the reasons why we need to use the local feature. It's a very complicated one actually, but sometimes you can, for example, suppose that you actually we are looking into this face recognition, right? And then sometimes actually some people wearing mask or they're wearing the sunglasses, right? Then we can actually based on the mask and sunglasses, we can hide some part of our face, right? But by using the local patch, then we can see there's some patch from here to there. Then we might, based on those one, against the occlusion, we can actually identify we can successfully do the face recognition. Occlusion or background clutter. It's very complicated image, but human can very successfully can see that actually these are this lady's clothes and this animal and some of the background one. But actually, these are the very difficult, the challenging cases for clearly to separate to identify each individual object here. Also, actually these are the chair, but even this chair, there are many intra-class variations, right? So then obviously they look very different. But if you look at some local patch, then there will be the chair back back is support that kind of one. So these are actually the example that why we need to have some of the image descriptor that are robust to this kind of changes, especially we look at the local image descriptors. Once we actually have the local descriptor, we can do the image search. Also, there could be I already mentioned that there could be many other applications. Here, one of the examples is image matching. This actually some of the I guess this is the Trevi content, and then here actually we can extract that looks different. The different angle, different illumination. But we can identify. This might be the even harder one. This looks very different, right? But we can identify local patch, and then if we can actually matching those local patches, then we can actually align them together. This say another example, image stitching. Here, basically local patch is nothing but we identified many of the interesting key point. Here we are showing the many interesting key point, and then the point itself does not give a lot of information, right? And then around that the key point, we actually look at the image patch, the patch, and then given that patch, we extract some of information, like what are the actual color distribution, what are the gradient distribution, something like that. And based on that descriptor, we can perform the matching between them. For example, here we can actually we can say that this matching to there, this maybe matching to there, something like that, right? Based on that, we can actually align them together. Then you can actually merge these two different images into the one. That's known as image stitching. So in this, basically image. So basically, we need to have the certain way of the algorithm that extracting key point and image descriptor in a same location. For example, if we can extract the local patch from here, also in this case, if we extract the local patch there, right? Then obviously they are kind of random, and then we cannot see that they are matching together or not, right? So basically, in this case, one may be the good key point or the local image patch that we can extract consistently from these two different ones. You might have different idea, but the one maybe say that what about this some sort of local this peak of the image, something like that, right? Local peak. If you look at local peak, we can actually extract it here, or there, or so we can here, something like that, right? Then there might be the higher chance that we can actually match them together, right? So that's the main reason how we can actually detect the same key point independently in both images, right? There should be repeatably detect this key point, and then once we identify key point, we need to actually first point we need to correctly recognize this corresponding the one, right? So basically that's also as I mentioned before, point itself is not useful information. We need to look at this image patch around the key point, and then we need to represent them in some sort of compact representation known as image descriptor, and then based on information we perform the matching. That's the actually main step. We'll talk about that one later on. As you can see, for extracting compute. Anyway, do you have any questions so far?
No.
Okay. There could be the very different the direction about extracting the image descriptor, but actually at this point there are two main directions. One is classical approach, right? Classical approach is mainly nothing but we actually manually design the whole image descriptor. We actually extract a lot of information, came up with a very interesting idea, right? And those techniques actually the design in image processing and computer vision field. One of the very well-known examples is SIFT, which will be discussed later on, maybe the next time. Also, there are some of the recent techniques also based on deep learning techniques. They actually manually design, but they actually more or less this data-driven. They're computing in a data-driven way. we look at actually there are a lot of images and we say that this patch, same thing. Then can you come up with a way? Can you come up with a way that they can actually they can be treated in the same way, same patch? It's kind of the learned approach, but actually they are not the random approach. Actually, in a way that they are inspired a lot by the many these prior manual crafted approaches. So in this class, I will talk about some of the well-known classical approaches, and then I will then followed by talking about the deep learning approaches. So I wish that you can see some of the connection relationship between classical and some of deep learning approaches. I believe that actually in recent days actually we are getting a lot of successes based on deep learning. But I believe that actually by combining some of the prior classical approaches with this one, I think that we can get a much better result. So there are actually many existing the manually created actually descriptors. We are not going to cover a lot of them. Many years ago I actually talked about those one, but right now I will talk about only a few of them. One of them is one of them I will mainly talk about this corner detector. But here same thing. Actually, the key point localization is very important. Basically, the key point should be repeatably detected across the same image, and we need to do this precise localization. I mean, there are many pixels away from this key point, then it's very difficult for us to match them correctly. And also, there should be interesting content, right? So early on, based on these goals for the image descriptor, they look at this kind of signal change. The image usually in the 2D, so they look at the two-dimensional signal change. And then early on, this corner treat that actually there may be the interesting feature. So actually for the corner there are very interesting information. So around the corner, the image, if you look at the image gradient, actually there are at the corner there are basically two very dominant direction. For example, here this is corner, right? So basically in the corner here you can see that at the corner we might get the image gradient from here to there, or from here to there, right? So actually that indicating that this describes that feature. Also corner in a way corners actually repeatable and distinctive feature. For example, if I ask you, can you find a point within this edge? I mean, how about pick a point within this edge, right? I might ask you, right? Pick a point within along that edge, right? Some people may say that I picked this one. Some people I picked that one, something like that, right? There could be many different ones. So it's not really consistent and repeatable approach, right? But how about I ask you find the corner over here. I mean, given this the rectangular shape, find the corner, right? Then some people find the corner here, corner there, corner there, corner there, right? But if there are many people, they might will just order upon only four of this corner, right? So it means that there are only a few these corner. Also, most of people can order upon this computed corner. So intuitively, that's why corner is turn out to be very repeatable and distinctive feature. And then it's the same thing. Basically, in this flat region, if we look at if we treat this flat is actually a key point, then if you look at the local patch, this local patch can go anywhere, right? Even though you go that direction, not much change, right? But if you look at the edge is the interesting feature. Edge could be here, but it could be there, it could be there, right? They're same thing, right? It means that some people say that this is some point, some local patch here, or some people say that this might be the one. But again, if you look at the corner, right? We can given this local image patch window, we can actually find one corner here, something like that. So this is the same thing actually. We can corner will be the very interesting one. And also this also explaining one main characteristic of looking at this corner within this one. If we shift this local window along any direction, you can see that there are a lot of these color change, right? Here, if you change along that direction, not much change. In this case, in any direction, you don't see the main change, right? That's That's the kind of the one of characteristics in terms of the signal change, right? So based on that idea, Harris corner detector actually came up with this idea. I will just briefly touch on the high level idea. Actually back then I actually derived a very detailed one, but I will show you some of the derivation on my book. In this class I will show you the only high level idea. The main reason is that basically I wish that we can save more time for this coming lecture about this deep learning. But if you're interested, you can look at the more detailed direction here. We want to look at this color change, signal change when you actually moving this window, right? So actually to do that, actually this Harris corner detector look at the autocorrelation function. It means that this is actually image intensity, right? Image intensity. We look at the when you shift this image along the UV direction, we adding x plus u and v. We actually we shift this some coordinate, and then we look at what are the intensity change, the change, right? And then we look at there are certain weighting function. For example, weighting function say that since we are looking to local image patch, we need to have the definition of locality, right? So to do that, we introduce some of the window, and then given this window, sometimes if the image, some pixels are within the window, it could be the 1, it could be, if it's outside, it will be 0, right? Sometimes you can use those Gaussian function. Typically, Gaussian is like preferred. Since actually, even though there are rotations, right? Actually, then it will be the rotation invariant, right? So typically, we commonly use the Gaussian. Also, the weighting functions are also gradually changing. While this actually very in this function there are actually this discontinuity, which is bad for the various computation. But anyway, that's the main reason why we have this one. So basically, this is known as autocorrelation function. We look at how the image change within itself. Then I skipped all the details, but if we take some tail expansion and so on, then we'll get back to this. We can approximate this prior function with this in this form. The uv is the shift, and then here we can actually have m. M is actually the eternal to second moment matrix. But to simplify our explanation, for the axis aligned corner, this m turn out to be this second moment matrix. Here ix is the gradient along the x direction. Iy is the gradient along the y direction. This is actually the ix square, right? Basically the square of the ix. Then this m turn out to like this, and in this axis aligned corner, this gradient, the sum of combination of gradient along the x and y, turn out to something like this. I mean, if you look at basically here, this in one of this corner, either either gradient along the x and y cannot be 0, right? But but if we combine them together, if we multiply them, then one of direction could be one of gradient will be 0, right? So it turns out therefore the kind of the x aligned corner, this turn out to be this could be some number here, some number, but the other one turn out to be 0 actually. Then based on this information, we can know that if we look at actually the local patch here and there, we look at this matrix, and then if we actually have this kind of some value here and there, we can see that actually there could be the corner, right? That's the main idea of this Harris corner detector. This both lambda 1, lambda 2 will be the non-zero if it is corner, right? Based on that, we actually we can basically you can see that it's manually designed, right? We look at this our problem, we somehow came up with formulation, and we can somehow design our own way define this corner, right? It's manually designed. And then again, basically depending on the lambda 1, lambda 2, if lambda 2 is turn out to be somehow big, it turns out it could be the corner. But either lambda 1, lambda 2 is 0, then it could be on the edge, something like that, right? For example, if this local window is located here, then basically we got the gradient along the y. Then the y could be the non-zero, but all the other one could be 0, right? Since the other direction gradient is 0, right? So for either one of the lambda one or the two is very small, then it turn out the other one is big, then it will be the edgy. Everything is small, then it's flat region, right? So based on by looking at the second moment matrix, we can actually classify the local patch whether containing corner, edges, and so on. That's the main idea of this Harris corner detector. And also I didn't talk about basically in the end we need to across this image we look at the local patch and we need to see that what are the probability to have corner, right? And then based on this one we actually came up with some sort of response function. The response function is nothing but if two value is getting bigger, the response function is getting bigger, right? Since it will be more likely to have a corner, right? So given this one, the two different images, we actually computed this corner response function. So, I'm not going to talk about the detailed equation, but main idea is that the response function designed in a way that it becomes bigger when lambda 1, lambda 2 is getting bigger. Then basically this response map, and red one actually bigger response function, blue one smaller one. Then given this one, we look at the local maximum. Then local maximum turn out to be if you look at local maximum, there will be the white dot. I think you need to see the slide. There will be the sum of these white dots. These are actually local maximum. And then we overlay the local maximum on top of the original image. You can see that we got this corner point, even this corner point here. Basically, we look at only the RGB change. Basically, the computed corner may not be different from our intuition. There could be many these corner here. Another example, you can see that it's reasonably work quite well, right? Another apply the Harris corner detector in this image. So basically, some of these corner detector. Another example here. Also, this was quite well and also used for for finding stereo correspondence. Given this stereo, we need to match, right? For computing these 3D reconstruction and so on. So at that case, also we can use this one. How about the rotation invariance, right? So you can see that also given this image, we rotate it, right? But seems like for example, here we got the rotation here, the corner point, and it's already off, but also we got some of one, right? Also, actually, we can also design I didn't talk about. I won't talk about the details, but we can also design the sum of second moment matrix, kind of invariant to the rotations. We can do that actually. We can very easily derive this rotation invariant approach. And other issues, scale invariance. But scale invariance, intuitively, you can see that it will be different, right? So for example, same this shape, right? This here, if we look at the small local patch here, you can see that this is actually the corner, right? But how about we zooming in? Then the original shape looks like this. Do you think it's a corner? It may not be the corner, right? So basically the main idea of this Harris corner detector is not invariant to scale. That's one of the issues of the Harris corner detector. So the shift actually designed in a way to invariant the rotation and scale of many other these geometric or photometric this change. We'll get back to the issue later on. Do you have any questions so far?
It seems like it's a kind of corner point matching, right?
Yes. We identify the corner, we try to match. Then we can, based on this one, we can also do the image search.
That's why it's no environment to image scale.
Huh?
That's why this kind of technique is not invariant to image scale.
Yes. So also it's not really scale. It's not scale invariant. So we need to think about it. Even though when you are zooming in, zooming out, same key point should be repeatably, constantly detected, right? So the shift that's designed in that way, we will get back that issue. So I hope that you can understand, you can actually know some of the related conference to our course theme. So I recommend you to. So if you go to our course homepage, there basically those conference CBIR, ICML, they are very well known, right? If you just Google search, and you can find a lot of even their conference, and you can see there are a lot of this accumulation of the paper, right? That way you can find the papers. and then I wish that you can understand the locally invariant features. We talked about Keypoint localization and Harris corner detector. It is manually designed, but later on, actually, there are recently we use some of the automatically learn the detector using deep learning. But if you're interested, so I'd like to, if you go to the class homepage, here, class homepage, if you click the some ongoing draft, I will try to update the some of more here. If you go to the this part, actually the data actually the early on, I actually had this corners as a feature. Right now you'll be under the chapter 1. Actually, I changed the chapter 2. You can see that more detailed derivation here to there actually. So if you're also we talked about the response function here. If you're interested, you can go over this one. But actually, I do not require to know that actually. I wish that we can also talk about more on the deep learning actually. So that's the let me see that actually. I have another slide here. Okay, next time I will talk about scale invariant, the fifth scale invariant region selection descriptor. And again, go over the next lecture slide. Try to come up with some one question. You can actually submit to here and go over the recent paper on image search and submit their summary. Do not copy this original the abstract of the paper. Just come up with your own wording. It could be the Korean English. That's okay. Just 1 or 2 paragraphs is okay. Just spend just 10 minutes, 20 minutes. So that way you can understand what are the relevant topics. Actually, yeah, you can submit here. Submit 2 summary of 2 paper by the next Tuesday class time. That's it. Thank you. Bye.